This is a question from our textbook. Question 12.5 says, which forces are intramolecular and which are intermolecular? Remember that if we have a molecule, let's say we have water, right? The forces that hold the water molecule together, these are intramolecular forces, intramolecular, okay? Which is another way of saying the bonds, the type of bonding in the molecule. Intermolecular forces in water, for example, would be hydrogen bonding. Okay, that would be an intermolecular force between two different molecules. Okay, well, with that in mind, let's look at the possible answers. Or the possibilities, sorry, the questions. A, those preventing oil from evaporating at room temperature. That would be intermolecular, wouldn't it? Right, because if it's trying to evaporate, it's trying to go from the liquid to the gaseous phase. You're not trying to break any bonds inside the oil molecules, whether they're in the liquid or gaseous phase, it's still the oil molecule. In B, those preventing from butter from melting in a refrigerator. Well, if we're talking about melting, then we're going from a solid to a liquid. This is going to be intermolecular again, intermolecular. Right, because it's still butter when it's melted. All we did was break the intermolecular forces that hold it together as a solid. Those allowing silver to tarnish. That's going to be intramolecular forces because we're causing the silver to oxidize. Right, we're forming new types of bonds. So this would be intramolecular. And the last one is those preventing oxygen in air from forming oxygen atoms. That would also be intramolecular. Intramolecular. Because we're preventing O2 from being broken to form oxygen. Right? We're preventing that from happening. You're actually breaking a bond there. Okay, let's move on from there. Try another practice problem from our book. This is question 12.19. From the data below, calculate the amount of heat in joules required to convert 22 grams of ice at -6 degrees Celsius to liquid water at 0.5 degrees Celsius. Well, let's take a look at what our heating curve would look like first. First, we would need to take the ice. So we're going to draw our heat absorbed over here. It's their temperature, degrees Celsius. First, we're going to take the ice and we're going to warm it up. This is a solid. Then we're going to melt it at 0 degrees Celsius. So we're starting at -6.00 degrees Celsius. Then we're going to warm it up. And then we are going to melt it. So for this, we're going to use the delta H of fusion, right? Because this is fusion going from a solid to a liquid. And then we're going to warm the liquid up. Okay, so this is our liquid. To calculate the amount of heat absorbed for the warming of the solid and the liquid, we use Q is equal to MC delta T. Q is equal to MC delta T. And then for the Q of vaporization, that's going to be equal to, here is going to be equal to delta H of vaporization times the number of moles. Okay, so we've got our Q1, Q2, and Q3. Our Q total is going to be equal to Q1 plus Q2 plus Q3. Let's plug in some numbers. Our Q total. Let's divide them up. Let's do each one separately because I'm kind of running out of space in this piece of screen. So Q1, let's do Q1 first. It's going to be the mass, 22.00 grams, multiplied by specific heat capacity for water. which is given to us, or sorry, for ice, which is 2.09 joules per gram degrees Celsius, and then the delta T is going to be the final temperature, which is 6 subtract -6, which gives us 6.00. I just do that in my head. And when you punch that in your calculator, you get the Q1 is equal to 276 joules. Let's do Q2. Q2 is equal to the delta H of vaporization multiplied by the number of moles. If I have 22 grams of ice, I've already gone ahead and calculated that the number of moles of H2O is going to be equal to 22.00 grams divided by 18.02 grams per mole for water, and that equals 1.22 moles. Okay, so it's going to be 1.22 moles multiplied by the heat of fusion, enthalpy of fusion. I'm going to convert that kilojoules into joules. So it'll be 6.02 times 10 to the power of 3 joules per mole, like that. And I get that my Q2 is equal to, what is it, 7350 joules. And then my Q3 is going to be equal to the 22.00 grams multiplied by 4.21 joules per gram degrees Celsius, multiplied by the final temperature is 0.5. The initial was 0, so 0.500 degrees Celsius, like that. And I get that my Q3 is equal to 46.3 joules. There's all of my Qs. I put them all together, and Q total is going to be equal to 276 joules plus 7350 joules plus 46.3 joules, and I get that my Q total is equal to 7672 joules, and that would be our final answer. This is question 12.27 from our textbook. The phase diagram for sulfur is shown down here. You can see that it's got 2 solid forms. It's kind of interesting, right? All the phase diagrams that we looked at up until this point always just had 3 phases, right? You had your solid, or you had solid, liquid, and gas, like that. But this one, you got 2 solid forms, rhombic and monoclinic. It's kind of interesting. Given the phase diagram for sulfur shown below, give a set of conditions under which it is possible to sublime the rhombic form of solid sulfur. So if we want to sublime, so sublime is to go from solid to a gas, and we want to do it for the rhombic form. Well, that would have to be down here, right? It would mean you'd have to warm the solid up, right? You'd have to go from here to here. So why don't we just write it like this? For A, we'll put heat the solid at a pressure less than 1 times 10 to the -4 atmospheres. Because if we're anywhere below, I'm going to highlight the line in green. If we're anywhere below this line that I have highlighted in green, okay, and we go and we heat it up, right, the solid up, we're going to end up in the gaseous phase. For B, it says describe the phase changes that a sulfur sample of sulfur undergoes at 1 atmosphere when it's heated from 90 degrees Celsius. So 90, if this is 94.5, so 90 is going to be down here somewhere. 90 to 450, so 90 to 450 is going to heat until I get to here. And so it's going to go from solid rhombic, then it's going to go to solid monoclinic. Okay, so I'm going from here, the rhombic, right? Then I cross over into the monoclinic. Then I cross over into the liquid, and then finally the gaseous phase. So then it goes from to sulfur liquid, and then finally to sulfur in the gaseous phase. Kind of cool. What is the strongest interparticle force in each substance? If I look at the first substance, okay, this is methanol, wood alcohol. Okay, if I draw the Lewis structure of methanol, which is this, who could tell me what the strongest intermolecular force that methanol could experience would be? Interparticle is the same thing as saying intermolecular. Who could tell me what the strongest intermolecular force that methanol would experience between two molecules of methanol? Is it a metal? No. Is it an ionic compound? No. Like Brianna says, oxygen, hydrogen, right? The strongest intermolecular force here is going to be hydrogen bonding. Okay. Let me ask you guys another question. Is methanol a polar molecule? Yes or no? Is methanol a polar molecule? Absolutely it is. Right? So it's also going to experience dipole-dipole forces. And every molecule experiences London forces. Okay? But the king of the castle is going to be hydrogen bonding. If I look at B, carbon tetrachloride, if you draw the Lewis structure and then draw three-dimensional structure of carbon tetrachloride, you'll see that it's a tetrahedron. Are there polar bonds in carbon tetrachloride? That's my question. Are there polar bonds? Yes or no? Absolutely, there are polar bonds. Right? There's a difference in electronegativity between carbon and chlorine. Chlorine is more electronegative than carbon, so there are going to be polar bonds. Here's my next question. Is carbon tetrachloride a polar molecule? Exactly. It's not a polar molecule. All dipoles cancel. Cancel. Therefore, non-polar. The strongest intermolecular force that carbon tetrachloride is going to experience is going to be London forces, or induced dipole. Okay, it's not going to have any dipole forces, and it's not going to have any hydrogen bonding. All right, and the last one is chlorine, Cl2. You draw the Lewis structure of chlorine. It's also nonpolar. There's no dipole here. It's a nonpolar molecule. So the strongest force that's going to be felt between two molecules of chlorine is going to be London forces. That's the kind of rationale you want to have when you're thinking about these types of problems. 12.43, which member of each pair of compounds forms intermolecular hydrogen bonds? If I look at A, well, first let's go over the requirements for hydrogen bonds. We've gone over this many times. You've got to have either a bond between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. There is no hydrogen, oxygen, fluorine, or nitrogen bond in dimethyl. This molecule is called dimethyl sulfide. Here I have an oxygen and a hydrogen bond, don't I? If you want to represent hydrogen bonding between two molecules, this is isopropanol, which is rubbing alcohol that you buy at Costco in case you get cut or something. The way you would represent that is like this: CH3, CH2, CH3. Draw the bond between the oxygen and the hydrogen explicitly. Show the lone pairs on the oxygen. Son of a gun, I need a new prescription. It's so bad. I made a mistake up here. There we go. There we go. Put the lone pairs in like that. And then draw a hydrogen bond. Draw one like this. You draw one like that. Okay, so there shows hydrogen bonding. And the next one, this is B. HF or HBr. Well, HBr can't be it, right? Because it's got no bond between hydrogen, fluorine, oxygen, or nitrogen. If I draw two molecules of HF, okay. Remember, you can put in your delta minuses and your delta pluses, delta minus, delta plus. So I have HF, I have another molecule of HF, delta minus, delta plus, and then I draw a hydrogen bond like that.